This lesson is for day 3 of graphing rational functions. Today we're going to introduce you to a new topic, and that's slant asymptotes. A slant asymptote occurs when the degree of the numerator is exactly one more than the degree of the denominator. So instead of having a horizontal asymptote, it's now going to have a slant asymptote. To find your equation for the slant asymptote, you're going to long divide by dividing the denominator into the numerator. As x gets very large, the remainder portion becomes very small, basically almost zero, so you don't really care about the remainder. You're just going to use the resulting term and discard the remainder, okay? Also, a slant asymptote is also called an oblique asymptote, so sometimes you see that in text or, in a website. You might see the word oblique instead of slant. It's the same thing. Okay, now, the first problem here, to graph this rational function, I'm noticing a couple things. One, normally we would say, oh, the degree is higher than the numerator, or in the numerator than in the denominator, so for the horizontal asymptote, we would say none. But now we know that since it's exactly one more higher, we actually have a slant asymptote here. So to find the slant asymptote, you are going to use long division. You're going to take the numerator, negative 3x squared plus 2, and you're going to divide that by x minus 1. So this is basically a review, of last year's algebra for long division. But one of the things you want to make sure you do is have a placeholder. See how I have descending terms here? It goes from x squared and jumps to 2. I want to make sure I put a 0x in there, and then that'll be my placeholder. So to long divide, I find how many times this term fits into my leading term. So I actually don't care about the rest of this polynomial here. I don't care about that, and I don't care about this right now. All I'm focusing on is how many times does x fit evenly into negative 3x squared. That is going to fit in negative 3x times. I don't typically always write the linear term above the linear term below it. You can or you can't. It doesn't really make a difference. Sometimes I see kids do it in front, and that's okay too, I guess. But some teachers get a little anal and they want you to write it above here. I don't really care as long as you can divide it correctly. So anyhow, so now that I've determined that it fits into their negative 3x times, now I distribute that back to this term here, okay, and I write that resulting expression underneath here, okay. So negative 3x times x gives me negative 3x squared. So I'm just distributing here, and then I'm going to distribute that as well to here. Negative 3x times negative 1 is a positive 3x. Now, I'm going to subtract that entire expression here. And notice how my terms match up. X squared is above x squared, and x is above x. If it's not matching up, then you can't, combine like terms, and that's how you know you probably don't have a placeholder or you've done something incorrect. So make sure always it matches up. So now negative 3x minus a negative 3x squared, that's going to cancel. Just remember you're doing 0 minus 3 here to get negative 3x, and then you can go ahead and bring down that positive 2. Now you're doing the same thing. You're finding how many times does x, but it's going to fit now into negative 3x. So you're always looking at that first term and how many times it fits into the resulting expression underneath that long division symbol. So x fits into negative 3x, negative 3 times, and if I were to multiply that back out and distribute it here, I would get negative 3x and positive 3, and then I'm going to subtract that whole expression here. These are going to cancel, and I'm left with 2 minus 3 to give me negative 1. Now, x cannot fit into negative 1 at all, so we're done with this long division. Now, typically you would rewrite this, since we're using long division here. If I were to rewrite that, it would be negative 3x minus 3 plus a negative 1 over x minus 1. Okay, or you could write that as minus 1 over x minus 1. So this is called your remainder. Now the remainder, like we said, as x gets very, very large, this is going to get really, really small, so it really doesn't matter at all. What we're looking for is this resulting linear equation. That is the equation of your slant asymptote. So your slant asymptote has an equation y equals negative 3x minus 3. Okay? So just to recap, to find your slant asymptote, you just perform long division. You take your numerator and divide it by the denominator. when you get your resulting polynomial expression, and it should be linear because we're going to be working with only solely linear equations. The slant asymptotes is linear equations. That's going to be your slant asymptote. Disregard that remainder down here. Okay? I'm going to go ahead and pause and get all the other information for this graph, and then we're going to go ahead and graph it. Okay, so I just went ahead and I graphed all, or collected everything else that we needed to know, like our vertical asymptote, our y-intercept, and our x-intercept. Now we have two x-intercepts, and that's because if we set our numerator equal to 0 here, we get two different x solutions here. So we have two x-intercepts at, oops, I forgot to square root that down here, but positive and negative root 2 over 3. Okay, so I'm just going to estimate where those are. I know that they're less than 1 because the square root of 1 is 1, so anything less than 1, the square root of that should also be less than 1 as well. Now, I'm just going to go ahead and graph like normal, like what we would typically see. The vertical asymptote is at x equals 1. And we have, let's do those in red, we have a y-intercept at negative 2. And we have two x-intercepts, one at positive root 2 over 3 and one at negative root 2 over 3, so something less than 1. Now that slant asymptote, when I graph that, that's just a linear equation, so I'm going to go down to negative 3 and graph slant asymptote here like so. Okay, and I'm going to also extend that, that vertical line as well. Okay, so maybe this looks a little bit messy to you, but all I did was graphed that slant asymptote negative 3x minus 3 here, and then my other points. Now, according to my graph, if it's going to have x-intercepts here and here, then my function, since it's supposed to always hug an asymptote, should look like this: dip down and then come back up. Okay, so now instead of, following a horizontal line, it's just following that slant asymptote. Okay, now this factor down here, this vertical asymptote. Sorry, it's so late right now. It's 11:45 right now. I'm so tired. Anyway, this vertical asymptote is only seen once, right? It's an odd degree, so this should jump on the other side, and your other branch should be down here. Okay, so it follows really this exact same rules, but now instead of the long run behavior following a horizontal line, now it just follows a slanted line. Okay, let's try number 2 real quick. Number 2 is, it's not really tricky, but I just wanted to throw this in there just to let you know that sometimes when the degree is exactly 1 more, it won't always have a slant asymptote like here. Even though that degree is exactly 1 more, if we factor the top, that would be x minus 2 times x plus 1 over x minus 2. Now you're going to actually just have a hole instead of having a slant asymptote here, because that factor completely cancels, and you're left actually with a linear function, y equals x plus 1. So we have a hole at x equals 2, and if we plug in 2 into our function, we get the point 2, 3. So I'm just plugging 2 in for here. Now when I graph this, I want to make sure that it's just a line, linear function, x plus 1, so I go up to 1, go up 1 over 1, but when I graph that, I want to make sure that I go back and erase, put a hole there, and write 2, 3 next to it, because there's a hole at the point 2, 3. Okay, and problem number 3, this one's a little bit trickier than most just because the denominator here is not factorable. So when you try to set your denominator here equal to 0 to find your vertical asymptotes, you're going to get something you need to use the quadratic formula for. So I'm going to go ahead and work that out. That's not really that important. We're not going to throw any questions at you like this, but I just wanted to do this question because of the long division. So I will find the vertical asymptotes. I'll find all the the x and y intercepts, but I do want to find the slant asymptote with you in real time. Okay, so slant asymptote. The reason why we know there's a slant asymptote is because nothing's going to factor out like we did in number 2, and we have a degree that's exactly 1 higher. Okay, so there's no horizontal. There's only a slant asymptote. So we take our 3x cubed plus 2, and we're going to divide that by x squared minus x minus 7. Now I want to make sure I have a placeholder here for 0x squared and 0x. So I need to have that quadratic term in here and a linear term in here plus 2. So now I look at it and I say, how many times does x squared fit into 3x cubed? It fits in exactly 3x times. So now I distribute that 3x to each one of the terms here in this polynomial, and I get 3x cubed minus 3x squared minus 21x. And that's just, again, coming from distributing here, here, and here. Now I subtract this entire expression. These are going to cancel. I have 0x squared minus a negative 3x squared to give me a positive 3x squared. 0x minus a negative 21x is going to give me a positive 21x, and I can bring down that plus 2. Now I do it all over again, looking at x squared and seeing how many times that leading term fits into this leading term here. It'll fit in exactly 3 times. So we have, again, to multiply that back out, we get 3x squared minus 3x minus 21. And now I'm going to subtract again that entire expression, and these are going to cancel. 21 minus this negative 3x gives me 24x. 2 minus a negative 21 gives me a positive 23. So this is my remainder because x squared does not fit into 24x. So that means that the equation for my slant asymptote is simply y equals 3x plus 3. So I'm going to go ahead, pause, and find everything else, and then erase this. But make sure you go back and just review that long division if that's still not making sense. Alright, apparently I wanted to make this problem really hard, but I just found all this information. I mean, really, we're not going to have something quite as difficult as this, even on an assessment. I don't think any of your homework problems are this difficult either, but basically we would do the same steps as we normally would. It's just not going to come out to be nice even integers. For example, the vertical asymptote here, after I use the quadratic formula, I end up with these two possible values for my vertical asymptotes. So this is approximately, because if you take -1 plus something that's larger than 5, because root 29, I'm just approximating that, that's in between 5 and 6. So when I add that to, you know, this -1 here, this is going to be a little bit larger than 4, so when I divide something a little bit larger than 2, this is going to be about 2 point something something, okay? And that's what I mean by 2 point dot dot dot. Now when I take -1 and I subtract 5 point something something, this is going to be a little larger than, or a little smaller, I should say, than -6. So this is -6 something divided by 2, so that should give me something that's a little bit smaller than -3. Okay, so this is about -3 point, I don't even know, you can make up a number of 3.5 if you want to. Okay, the x-intercept here is found by setting the numerator equal to 0, so I end up with this equation here, and I get a solution x equals the cube root of -2/3, and this is a real number, so we can use that as our x-intercept. The y-intercept is probably the only easy thing that I had you guys do on this problem, and that's just plugging in 0 and you get -2/7. Okay, so I'm going to start sketching this, and then the most important part is making sure you understand how to do the slant. Okay, so I went ahead and I graphed the vertical asymptotes in green and that slant asymptote in red. Okay, your graph does not have to be amazing or perfect, but make sure you obviously get the slope in the right direction and all that sort of good stuff. Okay, so now here's where the important parts come in. You want to graph your x-intercept and your y-intercept. Now, my y-intercept is a little easier to graph than my x-intercept, but my x-intercept should be less than -1, so I'm going to place that about right here. Okay. Now, looking at this, it doesn't really help me graph a ton. Now, I could, you know, find some numbers and start testing some points just to see if it lies, you know, in a positive quadrant, or if it lies underneath that line, you know, the x-axis. But I'm just going to take a guess here and say that it probably crosses this horizontal asymptote, or I'm sorry, the slant asymptote here. And the reason is because I don't see any multiplicities. I don't have the same term to an even number of times. Now the graph should look like this then, because on opposite ends they should go in opposite directions. So since this one is going down here at this vertical asymptote, this one should go up. So that's how I would sketch my branches. Another way you can think of it too is if, let's say you didn't think it went through, okay? You thought, okay, let's say it goes through this and comes back down like that. Now, the graph does not have any multiplicities that are even, okay? So I would have to graph that next branch then like so. Now this cannot be true, because then that would assume that I have an x-intercept. Okay, so that's how I know that it was supposed to cross through before, but this is how I can, you know, basically if I make the mistake of thinking it's supposed to look like that, Then I, draw the other branch and I'm like, oh wait, that's an x-intercept, and I only am supposed to have one x-intercept at the cube root of negative 2/3, which I've already got graphed. So that's how you know that that branch can't look like that, and the branch must look instead, if I erase that and go through, it must be down here. Okay? And then the other branch, of course, is here. And again, the same thing would have been true here if you thought that the branch was supposed to look like this, because it's supposed to hug those asymptotes. It can't, because it's going to have another blah 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 x-intercept. I'm really sorry, I keep making so many mistakes today. I am tired. It's now 12:02 a.m. on Tuesday night. I hope you're learning so much from this, because I hope I'm not confusing you. Alright, next problem. I would like you guys to try this one on your own and check with the key, okay? There's also another problem, a few problems actually down here, 5, 6, and 7, that I would like you guys to do. Just be careful on 5 and 6 what you do first. Make sure you're always factoring first. And then for number 7, just find the slant asymptote just to practice that you can do the long division, okay? All right, the last thing that we're going to talk about is writing an equation from a graph. So we're just writing possible equations for this particular graph here. There's some things that you want to notice every time you're looking at a graph. One, you want to look for the x-intercepts, you want to look for asymptotes, and any holes, okay? So there's a few things here that I'm noticing right away. One, I notice that there's a hole at x equals 4, which means that my resulting rational function here, and this is the graph of a rational function and not a polynomial function because it's got, all the discontinuities in it, but this graph should have this for the equation then. You're going to see x minus 4 appear in both the numerator and the denominator so that that factor can cancel out. We also see that the x-intercepts here are at negative 5, negative 3, and 1, which means that x plus 5, x plus 3, and x minus 1 should be in the numerator. Okay. We also see that we have a vertical asymptote at x equals negative 4 and 2 at x equals 2, so that means that x plus 4 and x minus 2 should be in our denominator. And there's another piece of information here that I have, well actually two more. I'm noticing that these go in the same direction when they approach x equals negative 4, so this should be even here. That should be an even multiplicity at x plus 4. And I also see that I have a horizontal asymptote at y equals 2. So if y equals 2 is the horizontal asymptote, then that only happens when you have the coefficient out in front and the degree the same. Okay, so if it was 2x cubed over x cubed, then these are going to cancel and leave me with that coefficient out in front. So I know I should have a 2 out in front, and I should also have the rational function here should always have the same degree on top and bottom. So I'm going to take that information that I have, and I'm just going to start writing an equation. And I'm just going to keep checking to make sure that it reflects what I have, written down here as well as what I see in the graph. So let's start. We have in our numerator x plus 5, x plus 3, and x minus 1. And in our denominator, x plus 4, we want that to be an even power, so let's make that x plus 4 squared for now, and x minus 2. So I'm looking at this overall and I say, okay, well, I have a degree of 3 on the top, right? X and x here, degree of 3, and I have degree of 3 on the bottom, so that satisfies this last part here, and I just need to add a 2. Now this, if you want, you can verify this using your calculator, but that's really all the steps that you need to do in order to get a possible equation. I'm not asking you for the equation of this graph, otherwise I would make you find the y-intercept, which I don't even give you, and do a little bit more algebra from there, but we're not going to have you do that. We're just going to have you provide a possible equation for this particular graph, okay? Alright, number 9, we go through the same steps. You want to look for any important information. I notice that I've got a hole at x equals negative 4, which means that I should see x plus 4 over x plus 4. Oh geez, you know what I forgot to do in this last one? Exactly what I was just talking about. We should also have x minus 4 over x minus 4 in here because these factors are supposed to cancel to create a hole. See, I'm making so many mistakes, my goodness. Oh boy. Alright, so coming back to number 9. So in case you didn't catch that, this should be the correct answer here. Sorry about that. Alright, in number 9, I looked at the whole already, at x equals negative 4, and I know that this, hopefully I don't forget that, but that should go in the final equation. I also have an x-intercept at x equals 1, which means that x minus 1 should be in the numerator. Okay. I'm also seeing that it doesn't go through the horizontal asymptote like this, so since it bounces, then this should be an even power. Okay, because it should have an even multiplicity there. Everything else is going in, they're going in opposite directions here at the asymptotes, for the vertical asymptotes. So there's nothing kind of spectacular or new about those, but the vertical asymptotes at x equals negative 1 and x equals 4 mean that I should have x plus 1 and x minus 4 in my denominator. Okay, so this is really the information here, and the last piece is just that y equals 0. So you want to take every single piece and try to look at it and look at it from all sorts of different angles to, analytically inspect your graph. If y equals 0 is your asymptote, then that means the degree of the numerator should be larger than the degree of the denominator. Okay? Did I just say that backwards? I think I just did. Oh boy, it should be it should be bigger in the denominator. I'm sorry. Okay, so degree on top, like if it was x squared over x cubed, this results in a horizontal line at y equals 0. Okay, so I just want to keep that in mind, since y equals 0 is my HA, my horizontal asymptote. I need to factor that in when I find my final equation. So I end up with y equals, since x minus 1 is in the numerator, and it's to an even power, I'm just going to make that squared. In the denominator, I should have x plus 1 and x minus 4. Okay. I also want to include x plus 4 and x plus 4, because those were my wholes. Now, looking at this, my equation actually looks like it should have a horizontal asymptote at y equals 1, because these powers are the same. This is to the first and first, so that would be x squared over x squared, which would result in a horizontal asymptote at y equals 1. So I need to factor in the fact that it's supposed to have a horizontal asymptote at 0. So what I'm going to do here is make one of these a higher degree, but an odd degree. Okay, because again, as it approaches x equals negative 1, it's supposed to jump to opposite parts, and as it approaches 4, same thing for the behavior near that asymptote. So in this case, I could have picked the x plus 1 factor, or a resulting equation could be the exact same numerator, x minus 1 squared and x plus 4, over x plus 1 times x minus 4 cubed times x plus 4. Squeezing that in there. Okay? So either one of those would do, just as long as we have the degree of the denominator larger than the degree of the numerator. Alright, last one is a polynomial function. I think that's just a review, so you should be able to do this one on your own. So please try that one and check with the key. Sorry for all the mistakes, guys. I hope you had a fabulous time making fun of me. Okay, I'll see you tomorrow. Bye.